So I guess we are going to start. People on Zoom, can you just report one more time if you can hear me? Perfect, thank you. So let us, thank you for confirming. Okay. All right, so welcome to ECE 560. We are in the winter 2022 semester. The course is Modern Control Theory, and this is lecture 1. Okay, so let's quickly give you an introduction about the course logistics before we move to the actual content. So I'm sorry, we are having some issues with the oops. So I'm your instructor for this course, and if you need to get in touch, my email is the following. Okay, so we have a TA or grader for this course. His name is Shahid, and you can also refer to him if you need help, and he's also going to grade your assignments, so you may have to contact him based on the requirement. So his email is the following. Okay, so the course format is going to be an in-person lecture. Plus there's an option for a Zoom meeting. Okay, so I hope everybody's safe during these times, and if you will, you can also attend on Zoom. Okay, so the office hours, because of the way things are set up right now, we will not have regular office hours, but if you need, you can schedule one by appointment via email. Okay, now some housekeeping regarding the course. There's a prerequisite here for the course, which is the precursor, which is ECE 460, automatic control systems. So it's expected that you have some understanding of control systems in general. Automatic Okay, so the textbook for the course will be Linear Systems Theory by Joao Hispana. It's also included in the syllabus that I sent you, and and good thing is that the book is freely available online, so you don't have to purchase it. You can actually download a PDF and start referring to the topics. However, the course is going to be self-contained, and if you go through the lectures, they should be enough to steer you through the course. All right, so now let's give you a structure of the grading policy and the kind of the assessment criterias. So you'll have a first thing is there is no exams, okay? So there's however, you'll have a series of graded assignments, and I'll just quickly write down what their distribution will be. So you will have quizzes. So the quizzes will be held via Canvas. So it's going to be bi-weekly quizzes. That means you have one quiz after 2 weeks. Okay, so you'll have a alternating set of assignments, like a quiz and a homework, and a quiz and a homework, and so on. So every week there's going to be either a quiz or a homework. And quizzes are going to be held in Canvas, and there's a practice quiz that I uploaded recently. So practice quiz and the idea is to give you an overview of how the quizzes will be, so you can try to attempt the quiz. It's not graded, it's just to help you see how the format of the quizzes will be. And it's due on Monday. Okay. Now, throughout the semester, approximately we'll have 6 quizzes. Okay, so 10 points each. And the style will be a multiple choice. Or numerical answers. And from all these 6 quizzes, at the end, one lowest graded quiz will be dropped. So if for some reason you end up doing poorly on a quiz or another assignment, there is this option that one of your lowest graded quiz will be dropped at the end. So don't ask for makeup quizzes or you were sick or something. That's your opportunity. Okay, so these quizzes will make up 30%. Okay, and then you will have homework assignments. Okay, so it's up to you. You can handwrite the homework or you can type it up, whatever you like, but it has to be uploaded on Canvas. And again, this is bi-weekly endeavor. Okay, so similar style, you'll have approximately 6 homework assignments. So we're trying to reduce workload by giving alternate weeks of homework. So one week you'll have a quiz and the other week you'll have a homework. I can say solutions can be handwritten or typed. And uploaded. So some of the homeworks will also include some MATLAB exercises. So MATLAB or Simulink exercise. And finally, one lowest graded homework will be dropped at the end. Okay, and the homeworks are going to comprise roughly 40% of the total grade. Okay, and the last thing you will have is the term project. So let me also take a couple of minutes here to describe what is expected from the term project. Okay, so what we are expecting is a self-contained project on control applications in general. Okay, so we understand that everybody is coming from different backgrounds and is working in different areas, so the project scope is open-ended. And can be based on your own preferences. Obviously, if you need help selecting projects, we can always suggest something, but it is really up to you to decide an application area and then use some of the control techniques to complete the project. And for projects, we will allow a team or so teams of up to 2%, up to 2 students can select one project. Okay, so if you want to do it by yourself, by all means you're welcome, or if you have a team member that you want to work together with, that is also an option here. Now, so a general kind of a instruction here is that you don't need to reinvent the wheel, right? So a lot of the times students come up with ideas that are already there are models that exist for those applications, and maybe that type of effort is not even required. So I would say no need to reinvent the wheel. Okay, so a lot of the times you will find that dynamical models are already available. So when I say dynamical models, they can be for applications like robotic arms, like other like vehicle dynamics, and so many other things. So people have developed dynamical models, and you don't need to start from the scratch. You can actually leverage existing results and existing models to actually do something which is a bit higher level than the ground, the absolute lowest level. Let me just clean it up here. Oops. Okay, so they can be used, but there must be some novelty in either your approach. Okay. Or application. All right, so this is going to be the remaining 30% of your, so there's 30, 40, and then oops, and then you have the remaining 30%, which is coming from the project. Okay, and also as a side note, in the project, I will say that there will be 3 main milestones. So I mean, this is going to be an endeavor which runs throughout the semester. So you will have a project abstract coming up first. Okay, and this is basically a 1-page description. Let me just clarify this. So it's description, submitted approximately 4 weeks into the course. So I will put a submission link on Canvas, which can allow you to upload this. So you'll see the date, and it's roughly after 4 weeks you are expected to submit an abstract of what you want to do. Okay, so it's not graded, right? So your project idea it doesn't have a grade, but will assist you to keep on track. In planning. And then you will have a midterm review. Okay, so that review will be basically a half-baked. Hello. Good morning. So that midterm review is again a few weeks before your final report. So it's going to be a half-baked project report. Again, it's not graded, and let's use another page. So it's but you have to submit it, and it's designed to really to keep you on track for a final submission. Okay, and after that you will have a final project submission. And it will have two things. One is the complete set of project deliverables, okay. That means a report in IEEE template, and the final thing is approximately 10-minute in-class presentation, okay, or a YouTube video for online students. Okay, so for the projects, the grade evaluation or the kind of evaluation criteria is as follows. So I just want to make everything clear up front so that you don't have ambiguity later on. So for projects, you will have novelty that will carry about 20%. It has to be technically correct, which will carry the majority, 40%. Clarity of so let's say clarity and presentation, this will carry about 35%. So most of the the score is towards technical correctness and presentation, but finally at the 5% remaining is for the oral presentation or video. Okay, so if you do the last bit, you get the additional 5%. Okay, maybe I can also write quickly some guidelines on how you can select a project. So maybe the best way is to select a project, is to think of an application area first. So for example, it could be anything of your interest. For example, you want to do autonomous driving, or you want to do battery algorithms, or you want to do UAV control. So it's first thing you need to decide is what is the area you want to work in. It could be coming from your work or from your research interests. So that's the reason we are keeping it open, so that you have the flexibility to select it based on your interests. And then I would say what you can do is you can search for already available implementations. So there's a lot of packages in MATLAB and other computational software. So all the control techniques that we will study, and also those which are beyond the scope of this course, are going to have some packages that you can use and play with them. So for simulating or implementing ideas. Right, so that's the key. If you're not able to implement things, then then again developing things from the scratch is going to be hard. So my suggestion will be to start off with some already available packages, and then you can add onto it and try to improve. And finally, you may have to read and explore material which is beyond what is taught in the course. Okay, so that's it for the course logistics, and at this point, if you have questions, you can let me know, and after that we can start with the course contents. Does anybody have a question? Also, people who are online, can you again confirm if you can hear me?
I can hear you, Professor, but I have a quick question about the presentation, the online.
Yes.
Is it possible for us to, does it have to be video, or can we presentation over Zoom?
if you can attend the lecture via Zoom, then you can do it via Zoom. I mean, you can record it offline on Zoom and share it, or it's up to you.
Okay.
Okay, but there has to be an oral presentation.
Okay.
I have a quick question.
Yes.
Quizzes and assignments are online, Professor?
Yes. So quizzes are on Canvas.
Sorry?
Quizzes are on Canvas,
Okay.
and assignments need to be handwritten and uploaded on Canvas.
So it's online.
Online.
There is no end term
There's no exam,
or no exams.
no midterm, no
Okay,
exam.
gotcha. Thank you.
Just a project and a series of quizzes and homeworks. Okay, I guess we can get started on the course contents. So, so this course broadly is on control systems, and when we talk about control systems, they are all around us, and probably you're also familiar with them from your previous courses or undergraduate. So the main idea of control is that you have an underlying system, right, that you need to exert some control on. So if you just want to say what a control system is, it's really it's an interconnection components forming a system configuration. That will provide a desired system response. Okay, so again, things here are still abstract because we haven't described what the system will be and what do we mean by the system response. So to make this a little simpler, let's start with a couple of examples here. So one example which you can all relate to is a temperature control system. Right, so what happens is nowadays everybody is using HVACs, and they have a temperature control functionality. So where what you do is you set a temperature that you want to attain, and then the HVAC turns on, and it will also turn off and on in a way that you achieve a desired temperature. So nowadays we have smart controllers like the Google Nest or things like that. So what happens is really you have a control system which has a certain response. So let's say there is a temperature here on the y-axis, and you're measuring the room temperature over time, and your desired temperature is this level. Now if you turn on or off the HVAC, then you will have a change in temperature over time, and it could have different trajectories. So one possible trajectory is the following. So let's say it increases from 0 and goes to your desired temperature. Okay, this is one type of response. Obviously you can have a steeper curve or a lower curve, but then at least this is one type of response you can have. We can have another type of response which can be the following. So your controller generates an input that achieves this type of response. Okay, so what happens is you actually overachieve your target, and then you turn it off, and then it goes down again, you turn it on, and then it goes up and goes down, so keeps oscillating until you reach your final configuration. Okay, so the question is, which one do we desire? Right, so that's coming from your design requirements, and then we want to translate them into a controller that can actually achieve it. So this is one example, but you can always relate this scenario to more examples, like like cruise control in vehicles. Right, so when you set the vehicle to a certain speed, again, that's a control system where you where the input is the acceleration and the achieved velocity is the output. Okay, so you will have similar kind of control system where you try to design that control input to do certain or to achieve certain response. There's so many other examples. You could think of active suspension systems in vehicles, right? So nowadays people want to exert some control over the suspension systems of the cars to achieve a desired damping that provides more comfort. So again, this is a control system that you need to design. Okay, so in this course we are going to study fundamentals that underpin all of these applications. Again, each application is specific to its own physical model, and that's not the topic of this course. But you can always go and find out the physical models of any type of system that you're looking at. So control doesn't have to be just a physical thing. It can also be in the electronics, like battery charging. Right. So nowadays you can see your cell phones have a certain charging profile. So there's a curve that tells you over time how the battery level went up, and then how it went down, and then you start charging again, and so on. So obviously it's not linear. Sometimes it can be like this, or in other shapes based on how you design the controller. And each type of response will have certain consequences on your battery life and on the performance of the battery. So the goal of this course is really to orient you with the tools that can help you design efficient controllers. And these are some applications also to help you decide what projects you want to do. Okay. And if you think of any of these applications, it has the same kind of behavior where you have to where you have something which you want to achieve, and there's a control input that can change how the output behaves. So you want to achieve a certain behavior, and then that's where the controller design comes in. There are so many other applications. You can find applications in robotics, in other areas like chemical process control, and even in energy systems. Right, so the control systems are really widespread, and they've been very well studied and evolved over time. And what we are studying is really the modern way of looking at control systems. So let's start with a representation of a system in very generic terms. So whenever we say a system, what we mean is that there is a process going on, right? So that process can be physical, that can be electrical. There's some kind of transformation going on, which depends on what the input is, and then that process basically generates an output, and we will call it Y here. Okay, so there is an input U and an output Y. Okay, and this process is the sometimes people also refer to this as a plant, right? Like a chemical plant or another type of a plant. Okay, so when we say systems, this is the general outlook, but it can have different type of properties and different classifications. So I will just quickly write down what are the general classifications. So systems can, in general, be classified as it's either linear or non-linear. So whenever we say that there's a system, we generally want to know whether that system is a linear system or a non-linear system. Okay, and then whether the system is a continuous time system or a discrete time system. Oops. Okay. Whether that system is represented in a input output relationship or something referred to as a state space. Okay. Whether the system is time invariant or whether it is time varying, right? And then we can also classify them in terms of the number of inputs and outputs that the system has. Okay, so number of inputs and outputs. So when we say number of inputs and outputs, we mean that there can be a single input and single output system. Okay, so that type of system is called a CISO system. These are terms that you might have heard of already, or you might already be familiar, but then there are other systems like single input, multiple output, which is called a SIMO. Then there can be multiple inputs, single output. That's called a meso system. And finally, you can have a multiple input and multiple output system, which is commonly referred to as a MIMO system. Okay. So now that we have seen a system and the different types of systems that we can have, we can actually look at the control of the systems. So one type of control is called one type of control system is called the open loop control systems. Right, so the thing is, we saw that there is a system with the input and that creates an output, and our goal is to actually design the control input. So one type of controller that you can build is called an open loop controller. Okay, so what does that mean? That means that there is no feedback in the system. So an open loop control system utilizes a controller or control actuator to obtain a desired response. Okay, and by that I mean that there is a again, let's make a process. Right, that process has a input and it generates an output, and the open loop controller will actually have an actuating device. So it will have an actuating device, and that actuating device actually gets the desired response as the input. Okay, so we tell an actuating device what is the output that we want, and that generates a U, and that U will go through the process and give you a Y. Right? So let's call this a Y prime, and hopefully, if the actuating device works correctly, your Y and Y prime will be very close. Okay, so let's take an example of what an open loop controller will be. So let's take an example of an open loop control of a turntable. Okay, so a turntable, let's draw a schematic diagram. So we have a battery right, that battery is actually trying to drive a DC motor, and there's a turntable on top of it. So the battery actually powers a DC amplifier, okay, and then that amplifier actually runs a DC motor, and that DC motor is actually driving a turntable. Okay. So there's a turntable on top of a motor, and you want to turn it to a certain point. So that means there's a certain number of angle that you want to turn the table. Right. Again, this is a very standard problem that comes in a lot of applications. Right. So when you try to adjust your seats in modern vehicles, there's a button that you press, and then your seat starts reclining, and at certain point you stop the button, and it just stops. But once you turn it, it turns until you stop it, right? So there is no feedback. There's no kind of mechanism to make sure that it achieves a certain position. So it's based on a manual kind of feedback. Now, if you want to turn the table at a certain speed, you can design a open loop controller. So let's see how that looks. Oops, I did something wrong. Okay, just give me a second. Okay, so if you want to design a open loop controller to achieve a certain speed of turntable, what you will do is you will have a desired speed that you want to turn it at, and that goes to the amplifier. That amplifier actually turns the DC motor. The DC motor actually drives the turntable. And what you achieve is the actual speed. Right? Again, you can relate it to the seat reclining in your car. When you press the button, you actually achieve a reclining speed, but you really can't ensure that you've achieved a desired speed. It depends on how good the motor is and whether it does the job or not. So there is no feedback, right? So you don't know what the actual the actual speed is, or whether that has been achieved or not. So it's just an open loop. You you input a set of requirements, and what you achieve is the output, and there is no feedback. So next thing which follows naturally is the closed loop system. Right, so closed loop is again a variant, and the only addition is the idea of feedback. Okay, the idea of feedback is actually really beautiful. when you pick up an object, it's really the feedback that is working, right? So your brain can process whether the object has achieved a certain height or not, and if not, then it provides a corrective action. Okay, so this is the a beautiful idea. Just give me a second. I'm trying
Can I
to.
attend the class in online? I'm not feeling good.
Yeah, sure, sure,
I'll do it online then.
sure.
Okay, I'm sorry.
Okay.
Thank you.
Sure. So feedback, as I said, is a beautiful idea. Eh, Whenever we want to achieve a desired response or a desired state, you first have to understand where you currently are, and then you need to provide a corrective action to achieve it. So, if you want to formally describe the closed loop control system, so it basically utilizes an additional measure of the actual output. So a closed loop control system utilizes an additional measure of the of the actual output to compare the actual output with the desired output response. Okay, and this measure is actually called the feedback. So this measure of the output is called the feedback signal. Okay, so let's see how the schematic looks like. So basically you will have a desired output response, and that is fed to the controller. Right, so the controller generates an input which actually goes through the process to create an actual output response. Okay, so now this actual output response, if you use a measurement device, right, so a measurement device or a sensor, if that is used, you can you actually feed back the output back into the input. right? And basically you subtract it from the desired output and feed back the difference. So the controller is actually driven by the difference between the desired output and the actual output. Now if the difference is 0, they basically you've achieved your target and no further change will happen in the output. Okay, but if there is a difference, you will this loop will continue to work and you will observe a change in the actual output until it gets close and close to the desired response. So let's take the same example of the turntable. Okay, so again you have the battery. Okay, that battery feeds a DC amplifier and that amplifier turns the motor so motor has a turntable connected to it, and the motor shaft has a sensor, right, or something called a tachometer that measures what is the speed, and that reading is fed back to the input, and then that closes the loop in the system. Okay, so if you want to see what the block diagram is, it's going to be a a desired speed that you want to, so it's like your reference signal. Okay, so reference signal is fed to the amplifier, and this goes to the DC motor. DC motor drives the turntable, and the turntable has some actual speed. Then this actual speed is actually measured by the tachometer. And you go back to the input, or not the input, basically you subtract it from your desired or reference speed, and that becomes the input. Okay, so I'm sure you would have seen somewhere these type of figures and diagrams that tell you what the idea of feedback is. And generally we look at systems that are linear, because that's where we can find solutions, and which are simple and easy to work with. So I'll just start with describing linear systems. Okay, so we've seen systems, we've seen that there can be open loop and closed loop systems, and let's look at other properties which I said, like linear or non-linear. So we can actually look at what is a linear system. Okay, linear system, as the name suggests, is a system that is linear. So meaning it satisfies the linearity properties. So we can say a linear system is a system that satisfies the principle of superposition. Right, so if you've seen linear systems in other areas like linear algebra, you would know that or in calculus, a linear function is a function that will satisfy the principle of superposition. And what do we mean by superposition? It's basically saying that if there is a system for which if you generate the output y, if a input u is given and there is a output z, if you feed in v as the input, then if you provide a linear combination, right? So that means a any linear combination, for example, then alpha u plus beta v, if you feed this to the system, your output will be alpha y plus beta v. Oh, beta z, sorry. So if u generates y and v generates z, then alpha u plus beta v will generate an output which is alpha y and beta z. So for any real alpha and beta. Right, so that's a very simple definition of a linear system. Okay, now the question is why use linear systems? Right? Because the world is not linear, why use Okay, so there's several reasons. One is that they are really simple. Okay, and we like simplicity. So simple and easy to work with. A second reason is that there is a well-developed theory around linear systems, and this theory is not only in the area of control systems but also from linear algebra and so many other developments that you can actually leverage, right? So that can be leveraged if you use a linear representation of a system. And the best part is that even nonlinear systems can also be approximately linearized. or maybe better way is to say they can be linearized locally. So if there's a system which is non-linear, you can always have an linear approximation to it within a certain small region. So locally you can have a linear representation of the system, and then the whole theory of linear systems will follow. Okay. Any questions before we proceed to the idea of state space models? No? Okay. So let's look at a very interesting idea which has actually revolutionized the study of control theory, and that's the idea of state space. So what I will say is system modeling. So up till now we've seen a system as a black box, and we didn't say anything about the system, but oops. And the state space Okay, so state space is really a revolutionary idea. Previously, before World War II, people used to primarily use the frequency domain approaches, right? That means input-output relationships and things like transfer functions, and those are really not easy to deal with, and also less intuitive. But after the World War II, people developed this idea of state space modeling, and that really changed the game. So that actually helps you leverage a lot of your linear algebra and other ideas into the design of control systems. So we'll take an example where a simple system can be modeled using state space. Some of you might already be familiar with state space representations, but we can do a quick refresher here. So let's take a mass spring system example. Right. Obviously, mass springs are part of a lot of different systems, a lot of different applications like suspensions and dampers and so many things. So we're not looking at the exact application, but generally, if you have a mass spring system which has a spring extension of x, and the mass is let's call it small m, and this is the input or force u, then this type of system you can have two physical laws applying to it. So the first one is that force, which is the Newton's second law, right? So F equals ma, right? So that's basically the spring force on the mass plus the friction plus the external force. Okay, and this is really a high level abstraction, and that total force is equals to the mass times the acceleration. Okay, so the spring force is actually minus kx, which is coming from the Hooke's law, right, in physics, and the friction force is equals to minus rho x dot. Okay, and that's coming from the Stokes law. Now, if you start writing down the the equation of motion, so basically the sum of the forces is equals the mass times the acceleration. So what we will have is a m times the acceleration will be the double derivative of the displacement, right, and this is equals to minus kx minus rho x dot and plus u, right. The external force is just u. So this is just an example here to show you how we can get to state space, but you'll not be required to do any of the modeling in this course, right, because this is a topic beyond the scope of this course. You can find models, but the whole idea is to understand how the output changes when you change the input. So if this was the equation of the input and output, this is a differential equation, okay, and we'll see how we can transform this into a linear system or linear ordinary differential equation, and also in the state space form. So let's try to write this as mx dot dot plus kx plus rho x dot. Actually, just let's write the rho x dot plus kx equals to u, right. So so let's call this as a, so let's x dot equals to v. I like just a substitution. So then m v dot, right, or if you divide throughout by m, it's just going to be a v dot plus rho over m v plus k over m let's keep it as x, right, and then equals to u over m. So the system will be defined by x dot equals to v and v dot equals to minus k over m x minus rho over m v, and there is a plus u over m, right. So that's your system. Okay, so if you have this system, you can actually write this in a matrix form. So you can say if you have a vector x and a v, xv dot is actually equals to a matrix so x dot is just a v, so you will have a 0 and a 1 here, and v dot is minus k over m x and minus rho over m v, and then there is a 0 1 over m u. Okay, so this matrix representation is actually called a state space form because it tells you how the states evolve over time. So this is a linear differential equation, and let me write the general form of the state space. So in general, the state space representation is as follows. So let's say you have a vector x1 dot, x2 dot, and so on up to xn dot. So these are n states, and these are evolving over time according to a linear differential equation. So you will have a matrix A, right, which is an n cross n matrix, and then you will have a vector of states, and then there will be a matrix B, right? So this is an n cross m matrix where m is the number of outputs and n is the number of states. Okay, so there is a u outside this, so u1 um, so there's a vector of inputs. Okay, so in general, if you want to write this, you will say the vector of states evolves according to this equation, which is x dot equals ax plus du, and the output is y equals to cx plus du. Okay, so this is the let's say this is the state equation, and this is the output equation, right? And the x is the vector of states, and the u is the vector of inputs, and in this whole block here basically these two equations are called the state space representation of a linear control system. Okay, and this is actually developed by Rudolf Kalman, who is a famous control theorist. So Rudolf Kalman. If you heard the Kalman filter, this is the person who's actually behind the state space modeling and furthering this idea. Right, the frequency based methods or the frequency domain approaches have been there for a long time, but after Kalman came in, he started pushing for this state space, and there's several benefits that you will see in this course, and it also helps simplify a lot of things. Okay, so we can take another example here, which is an electrical system. Okay, so we saw a mass spring system before, but this time we can actually look at an electrical system, right? For people who have studied electrical engineering or a course on circuits will be familiar with these type of schematics, and the beauty is that state space methods are really general. They are able to model mechanical scenarios, they can actually model electrical scenarios, and so on. So the theory is really generic and can be used to solve a wide variety of problems. Okay, so right now, as part of this lecture, we are just trying to bring a system into a state space form, and once it is in state space form, we will first analyze the system, and then we will design a controller, I mean the input U, that will help steer the system to a desired state over time. So remember, this is a dynamic scenario. There's a circuit where you have different type of components, and over time there's an evolution of voltage and currents. So let's say this is a current source U, and you have a resistance R, and you also have a inductor, right? So there's an inductance L, and then you have a capacitor which is charged, and the capacitance is C. So that's the circuit you are looking at. And in these type of circuits, you have to first decide what the state variables will be. Right, so the most important thing whenever you develop a state space model is to first know what is the state variable. And obviously you can pick up different quantities, and accordingly your state space model will be different, but it will still be the same system. So for example here, let's say the current through the inductor, which is referred to as IL, let's call it the first state variable, and then the voltage across the capacitor, let's call it Y. That's the second variable. Okay, so let the state variables be x1 equals to IL and x2 equals to Y. Right. And basically it's not the state variable, but it's the it's the output, right? But let's call the output as the second state. So So first thing is the voltage across the inductor. So we can directly write from Kirchhoff's current law. Again, you don't have to know all of these, but I'm sure people who are from ECE background, they are familiar with these things, but system modeling is something that a domain level expert is going to do. So oftentimes you don't have to really bother with modeling the system. When you work with a particular system, let's say you work with a robotic arm, or you work with a damping system, you basically know what the system model is, and oftentimes people have already developed state space representations, so you actually work with them. But just to give you a introduction of how people enter the state space world, we are looking at this type of derivation. So from this is not the current law. Basically, before even doing this, you can say that the voltage across the inductor x2 is of t is actually L times the derivative of the current. So you can say it is L times IL dot, right? And or maybe let's write it as L dIL over dt, right? Which is saying it is L IL dot, okay? Or in other words, because IL is x1, so x2 of t is L times x1 dot of t. So this is your first equation. And now from Kirchhoff's current law, which says that the currents entering and leaving the particular junction have to be zero, we can say that the I mean, if you do it at any of this point, basically the current through the resistor, which will be the voltage divided by the resistance, we can say it is x2 of t divided by r plus x1. x1 is the this thing here, right? So it's x1 of t, and then finally it is c times the derivative of the voltage, so c times x2 dot of t. It's equals to the u of t, right? So currents entering this junction should be equals to the currents leaving the junction. Okay, so if you have this equation, then what you can say is so let's call this 2. So from 1, basically you can say that x1 dot of t is 1 over L x2 of t, and from 2 you can say x2 dot of t is equals to minus 1 over c x1 of t minus 1 over rc x2 of t plus 1 over c u of t. Right, so if you want to convert this into state space form, right, it will be x1 dot x2 dot is actually equals to a linear combination of x1 x2 and plus an addition of the input signal. So x1 dot is 1 over L x2, and x2 dot is minus 1 over C minus 1 over RC, and then there is 1 over C here. Right, so this is your matrix A, and this is your matrix B. And remember, there's another equation which is y, and y here is simply x2. Right, so what you can say is so your C matrix is going to be, so let's write it down as a vector form. So again, you will have a x1 x2 here, and you will have a u. So your y is simply x2, so you will have a 0 and 1 here, and you will have a 1 by 1 matrix which is 0. So this is going to be your C matrix, and this is your D matrix. Okay, so do you see the state space here? I mean, in general, you will say x dot equals ax plus bu, and y equals to cx plus du. So d here is 0, and the matrices A, B, C are labeled. So is the state space representation. Now the beautiful part of the state space representation is that you don't have to go to any input-output relationship. You don't have to go to transfer functions. Everything is preserved here. If you want to actually get the transfer function, you can still use this. And the good thing about this one is you can see the internal information of the system. You know how the state evolve based on the inputs. So for example, by looking at this system, I see that the input only affects the second state. Right, so the second state evolves according to this relationship, and the first state evolves according to the second state. So even though the input is affecting only x2, but indirectly it also changes x1 over time. So looking at a complex system has become easier with a state space representation, and in the coming lectures you will see how the internal details can be figured out by just looking at the matrices A, B, C, and D. Right, and then you basically leverage your knowledge of other fields like the linear algebra, and that defines a lot of the properties of the system. Now we can also look at the other example, which is of a pendulum. And a pendulum example, again, is a very classical example to look at when it's about linear control systems. So there's a pendulum with a certain mass and a certain angle. So there's an angle of suspension, which is theta. There's an L length, and there is a mass, which or let's say the weight is called mg. Okay, now here an external torque is Te, and there's a force perpendicular, which is mg sine of theta. Okay, now if you equate all the torques, so let's write down the total torque. It's the pendulum torque plus the external torque. Okay, so if you look at the total torque, it's going to be I mean, if you compute it using the force times the length, then it turns out to be ml square theta double dot. I mean, you can look at this from the physics literature, but I'm just going to write it here to give you a sense of how things are derived. And the pendulum torque will be minus mg sine theta times L, and a external force, which is Te, right? And that's it. So so interestingly, this equation is a nonlinear equation, right? So you have a theta double dot equals, if you divide by ml square everywhere, you will have minus g over L sine theta plus 1 over ml squared Te. Right, so now this is a nonlinear equation. And why it is non-linear? It is not because of the theta double dot, it's because of this thing here. Sine theta is non-linear function of theta, right? So ideally we would want to have theta, theta dot, and so on, theta double dot. They are all fine because you can always convert them into a linear differential equation. But the moment you had this sine of theta, you cannot really use your linearity anymore, so you have to do some transformation here. Luckily in this case, if theta is small, then sine theta is approximately equals to theta, right? So that means, you know, if theta, and this is so this is your, let's say this is your sine theta, and this is theta, then you see there is a, you know, very close match in this region. So if theta is So if theta is small, then you can actually use the linear dynamics. So let's say, so therefore for small theta we can convert the dynamics as follows. So you will have theta double dot equals minus g over L theta plus 1 over ml squared Te, and then you can say let so let theta 1 equals to theta and theta 2 equals to theta dot. Then your equations can be theta 2 dot or theta 1 dot. So theta 1 dot is theta, so and so basically there is no theta, right? So theta 1 dot is theta dot, right? Which is equals to theta 2, and theta 2 dot, oops, let's see what happened. Okay, and your theta 2 dot is theta double dot, which is equals to minus g over L theta is theta 1 basically, and plus 1 over ml squared Te. So this gives you the state space representation where you have theta 1 dot, theta 2 dot in a you may confuse it with a Q, so let me just theta 1, theta 2 dot is in the matrix form. You can write it as 0, 1, theta 1, theta 2 minus g over L 0 and plus 0, 1 over ml squared Te. Okay, so you see that with a simple approximation we could actually convert the nonlinear system into a linear system, and again we have ended up in a state space representation. So generally this is the problem that you will see in a lot of situations, that the control systems are nonlinear, right? So in general, whenever you have in a real world, you look at a control system and it turns out to be nonlinear, which means that if I write the general form, it will mean that we will have x dot equals to some function of the state x and the input u, right? So that f may not be a linear function. So f is not of the form, it's not of the form ax plus bu, right? So f is not a linear function of x and u. So then what do we do? Is there still a way that we can avert this difficulty and and still be able to work with the system. And it turns out that yes, there is a technique which is called the linearization of nonlinear systems. Okay, so how do we linearize the system? So let's look at the technique. So assume that we have a system, right? Okay, which is described by x dot equals to some function of x and u, where x is a vector of states, right? So you have x1, x2, all the way to xn, and we have the vector of inputs. Obviously you can have different number of inputs, so let's say there's m inputs, and the vector u represents all the inputs, and the function f can also be a vector function, so it's also an f1, f2, all the way to fn, because you have n states, so you can have n different functions. So we know from the Taylor series expansions that your f, which is a nonlinear function, can be approximately written as a linear function around a point. So Taylor series expansion around a point x0. So if you want to approximate the function, then it's going to be f at the x0 plus f prime at x0 times x minus x0 plus half f double prime x0 x minus x0 whole squared, and so on, right? So obviously we want to approximate with a linear function, so we will ignore the higher order terms. So the fx will be approximately equals to the f at x0 plus f prime x0 times x minus x0. Right, that's the Taylor expansion. Okay, so assume x equals to 0, u equals to 0 is an equilibrium, right? Because the condition is that if your input is 0, then your state should also be 0, and that should be an equilibrium point. Input is 0, nothing should change. So that is the f 0 and 0 should be equals to 0. So that's like a boundary condition. Okay, so now let's say we have a set of functions. So for x1 dot equals to f1 of x and u, and x2 dot equals to f2 of x and u, and so on to xn dot equals to fn of x and u. We will have fi of x and u equals to fi 0 0 plus f and then a derivative curly fi over curly x1 0 0 x1 plus so on all the way to curly fn by curly xn of at 0 0 xn. Okay, plus there's also the input, so we will have curly fi 0 0 u1 by curly u1 plus curly fi of 0 0 over curly um times um. So the so that's the linearized, I mean, if this is the function approximation, then if you write it in a matrix form, it will be like this. So the linearized state space model is the following. It's just the translation of this into a matrix form. So you will have x dot equals to ax plus bu, where the aij is the curly f I over curly xj, and important thing is to ensure that x equals to 0, u equals to 0. Right, so if you take the derivative and then you substitute x equals to 0 and u equal to 0, because you are linearizing it at the 0 0 point. And the bij is equals to the curly fi divided by the I mean, I can change it actually. Instead of ij, let's call it ik, and curly uk. And again, important thing is x equals to 0, u equals to 0. Right, so substitute in the derivatives. Okay, so that's the general procedure, but we can do a quick example here to give you an idea of how to actually do it when it comes to the to a real function. So let's do a example. and so let's say pendulum revisited. So remember, the pendulum example had a state space model. Theta 1 dot equals to theta 2, and a theta 2 dot equals to minus g over L sine theta 1 plus 1 over ml squared TE. Right, so remember, here there's a nonlinearity because of this function sine of theta. So if you look at this function now, you can say that, okay, this thing here is the f1 of theta 1, theta 2, and TE, and this thing here, it's actually the f2 of theta 1, theta 2, and the TE. Okay, and your goal is to, so your goal let me write it in blue. Is to convert this into linear state space, right? Which means that you have to say, so you have to write down a form which says theta 1 dot theta 2 dot equals to some matrix Aij theta 1 theta 2 plus, right, so there's some Bik here, and there is a Te sitting here. So how do we find the Aij and Bik? We saw the process here. We need to take the derivatives of the functions and substitute states as 0 and inputs as 0. So let's try to do it. I mean, in this example, the matrix A, so A will be curly f1 over curly theta 1, and curly f2 by curly theta 1, curly f1 by curly theta 2, curly f2 by curly theta 2. And you have to remember that in each of these derivatives you have to put theta equal to 0 and Te equals to 0. Otherwise you will not be able to get the right results. Okay, so maybe let's see what is the f1 and f2. Right, so f1 is theta 2. Let's go to the next one, and so remember, the f1 is equals to theta 1, f2 equals to minus g over L sine theta 1 plus 1 over ml squared Te. Okay, so let's see what is curly f1 over curly theta 1. Okay, I need people's help right now. So I need 4 derivatives, and you need to help me figure out what are these derivatives. So if you've been not paying attention, now is the time to look at this example. So what is the curly f1 by curly theta 1? The thing here.
Is it one?
Yes, it is 1. And obviously we had to put theta equal to 0 and TE equal to 0, but it's not even required here, so that's okay. And what is the thing here?
Zero?
Yes, it is 0 because there is no theta 2 here. Okay, and again you had to put theta equal to 0, TE equal to 0. Okay, next one is the equation here. What is the derivative with respect to theta 1?
Minus g cosine theta 1 over L.
Okay, so minus g over L cosine theta 1, and not to forget that we had to put theta 1 theta 2 equal to 0 and a TE equal to 0, right? So it turns out to be
Minus G.
Minus g.
yeah, so it's just minus g over L because cosine of 0 is 1. And the last one,
This one was zero.
so it's 0 because you don't have any theta 2 there. Okay, so your matrix A here will be 0, 1 minus g over L and a 0 here. Okay, and the matrix B by the linearization formula we saw is curly f1 divided by curly u or curly TE, because u is just renamed as TE here, and the second one is curly f2 by curly TE, and remember to put you have to do the substitution after taking the derivative. So so let's again do the exercise. What is curly f1 by curly TE, and what is curly f2 so what? Perfect, this is 0, and
MS
1 over ml squared. Okay, obviously you had to put these things, but these are luckily not needed, right? So we are just left with a 0, 1 over ml squared, right? So if you notice, we have ended up in a state space representation which is exactly equal to the approximation that we were thinking of previously. So there's theta 1 dot, theta 2 dot, and we have a 0, 1 minus g over L, right, plus a 0, 1 over ml squared TE. So take a close look at this and I will show you the one that we did previously. A couple of slides back we have a third example on the pendulum, and if you notice, this is exactly what you get when you linearize the system around 0, right? And the good thing is you always linearize systems around 0, and the reason is because you when you use a feedback control system, you always want your input signal to be 0 because you're comparing against a reference signal. So the system input is always reference minus the current state, and that should be as close as possible to 0. So linearizing the system around 0 is mostly the case, and these tools will come in handy. So no matter how nonlinear a system is, if you do feedback control, you will always need linearizing around 0, and hopefully the whole theory of linear systems can be leveraged to design controllers for any type of systems. Okay, so I guess this is all for today. I will write down a summary of what we've seen today, and I'll just give you a pointer on what to do next. So so control systems, as we saw, have widespread applications in our daily lives, right? Systems around us. So we've seen some examples today, but if you notice around you, you will find much more applications of control systems. Okay, and in the modern vehicles, you will see many control systems working seamlessly within your driving and your cabin. I gave you an example of an open loop control where you adjust your seat recliners, but if you look at the climate control systems, that's more of a feedback control, because you set a desired temperature and the vehicle automatically adjusts the fan, the air conditioner and other components to achieve that desired temperature, right? So there is a sensor that determines the current cabin temperature and compares it with the reference that you have set, and adaptively adjusts the fan speed and other actuators. And similarly, you see your cruise control system, which attains the speed and again, the response can be very different. The car can abruptly move to accelerate very quickly to the desired speed, or it could do it more gradually, and so on. So there's obviously that design element there that manufacturers have worked out, and they look at things like comfort and other metrics. And just to name another example, you have the adaptive steering assist controllers. Again, what they do is they bring you back into the lane that you're already in, and again there is a reference that you need to achieve, and There is the control input that's coming from the controller, and in this course you will learn how to do things from a control system perspective, from a controller design point of view. And the starting point or premise is that you have a state space representation, because there's a lot of tools that you can work with once the system is already in a state space representation. So we also saw that a linear control systems are easier to study, and these systems really they go a long way in the design of stable systems. Okay, so there's so many other properties like stability and controllability and other things that we will study in the upcoming lectures, and all of these are for linear systems. And if systems are non-linear, you can always linearize them, and that will give you an approximation of the system at the origin. Now, the system modeling, right, is the art, right? So that's the requires technical and domain level expertise. So modeling is beyond the scope, right? So of this class, and if you take a system and you search the literature, you can find a lot of different models which can have arbitrary level of detail, and sometimes you want to abstract all of it, and there are some abstractions available. I can give you one example here. So oftentimes abstract models are used. For example, there's something called unicycle. For modeling a robotic platform. So unicycle is a let's say a robotic platform. So that's the so assuming there is a robotic platform, right? Like a robo vacuum or something like that, which has two wheels and there's one common axle, and if you want to model the dynamics, there's also simplistic models where the state can be the heading and the angle, right? So you can use these to so you can change the angle, right? Angle basically turns the platform, and the forward motion actually moves it forward. So two states can actually model a robotic platform. So you don't have to go to all the details of what are the mass and the other inertial components, but you use some abstraction, right? Other times people just use a abstraction like a particle, right? So they just use a kinematic model to abstract the scenario and use it to design control algorithms. Later they can actually be translated into as much detail as you want. But initially, if you want to move a robot from point A to point B, you need an abstracted model, and you basically design a controller to move it from A to B in a certain manner. And when it comes to real implementation, then you can translate that controller into an actual input based on what the system parameters are. Okay, so we've seen linear systems, and we've seen linear systems, but we said can actually be linearized to use the same theory developed for linear systems. Okay, so that wraps up the lecture today, and the next lecture we are going to probably look at some state space models and their relationships with transfer functions and how to solve those type of linear systems and so on. Okay, so I hope you found the lecture informative, and let me quickly give you a set of actionable items. So for next, so basically there will be a practice. So let's say the announcement. So number one thing is the practice quiz. There's a quiz which is uploaded on Canvas, and so that's going to give you a template for the upcoming quizzes, right? So based on your availability, or when you find the right time, you can go and try to solve that quiz. It's a 10 questions multiple choice quiz, and it is due on Monday, right? 11:55. So by Monday you can solve it. It is not graded, okay, so you don't have to really worry. I mean, if you solve it, it's going to give me an idea of what your preparation level is, what is your background, how much can you or do you grasp the content. It's not based on today's lectures. General questions on control, maybe by the end of the course you can answer all of them, but right now it's just to assess whether you can figure things out or not. Okay, so try to do it by Monday, and I would say you don't have to do it very instant, but start thinking about your projects, right? So if you want to start your research online, search some articles. If you already have an idea in mind or a field in mind, you can try to look up some literature on I quickly explore, and maybe also look at teammates, right? Okay. And then I think homework will be uploaded next week, right? So homework 1 will be posted after next lecture. And you will have 1 week to submit. Okay, so remember, no late submissions and all this undergraduate behavior. Or there will be a link on Canvas. You upload your work there, and if you miss a homework due to some reason, there's a provision that there's 1 homework and 1 quiz will be dropped at the end. So try to make use of that. Otherwise, don't come in and say, oh, I missed this and I want to redo it. This is not a undergraduate course, so try to be more professional. And regarding textbook, I already told you it's online, and you can get the entire textbook. Next time I will try to refer to sections in the textbook, but if you will, I can provide reading material from the textbook after every lecture. So some sections of the text I will post okay. So I guess that's it. If you have questions, let me know. You can always reach me by email, and but if there's something you want to clarify right now, just that's your opportunity. It's good. Yes, go ahead. Yes, yes, you're always welcome if you want to attend in person.
Professor, you will be posting these notes from today's lecture, correct?
Yes, after every lecture I will just post the written notes. Next, I think there's some issues this time with the technology, so next time I'll try to do a little better. Okay, anything else?
So one more thing, regarding this project report, so we can make email of 2 or 4, or it's only we can make it with like 2 people, or we can do the one.
You can either be 1 or 2, so you can be up maximum 2 members. You cannot have 3 people. And I think when you do team projects, so it's it doesn't need to be said, but you have to be clear about what is the contributions.
Yeah.
It should not be the case that one person is doing everything and the other person just sit dormant. And remember, I think the ethical code of conduct, I don't want to repeat it, but sometimes students just copy material off the internet and present it in the project reports, and I just want to tell you that the final projects will have a plagiarism test, so if your reports are plagiarized, then you will be penalized for the project. Okay, so in the past, I've seen projects where a high percentage of the reports were actually copied from online sources. So I've had I've given them a harsh penalty and penalization in their grade. So so everything you do, it should be your own work, right? Even if it is bad, I don't really penalize that much, but if it is plagiarized, I think that's a serious issue. Okay, other than that, I think if you ever need help, just send me an email. If you want to have an office hour, you can schedule it with me. We don't have a regular schedule, but based on your need or your specific circumstances, we can always schedule a meeting time. All right, so are you guys able to see the screen? Hello?
Yes, we can see. Yeah.
Oh, you're seeing my computer. Okay, perfect. All right, so let's talk next week then. And I hope you all have a great rest of your week.